Good afternoon. I'm Arun Serafin, Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. Thank you to all your attendees for your support of NDIA and ETI, and thank you for joining us for today's webinar, GPS 101 with Dr. William Bowder. The Global Positioning System, GPS, has become an indispensable part of daily life, so much so that the term is universally recognized. Most people have a basic understanding of GPS as the technology that powers the navigation apps on smartphones and in vehicles, guiding not just everyday commuters, but also pilots and wilderness explorers. Beyond civilian use, it's pivotal for military operations, offering unmatched precision, the intricacies, and strategic advantage. Despite its pervasive presence, the intricacies of how GPS works remain a mystery to many. What exactly is GPS, and how does it achieve such remarkable feats of localization and navigation? This webinar is part of our Tech 101 series, where we present complex technological concepts as introductory webinars with a focus on their national security implications. Some administrative remarks before we get started. First, all attendee lines are muted. Second, if you have a question during the webinar, you can submit your question in the question box in the webinar panel at the right side of your screen. We'll do our best to get through all the questions during the Q&A at the end of the presentation. We're recording today's webinar for members unable to attend and for any member who wishes to review the material at a later date. Within the next few days, we'll also post the slides and the recording to our website and our YouTube channel. I want to introduce our speaker. Will is a senior physicist with the Government Accountability Office, GAOs. He's with their Science, Technology Assessment, and Analytics, STAA, mission team, where he evaluates emerging technologies and technical government programs and advises Congress, congressional staff, and policymakers. Since joining GAO in 2019, Will's worked on a number of technical areas, including GPS, modernization, and alternative position navigation and timing, PNT, in the Department of Defense. Prior to his time at GAO, Will worked as a program manager, technical advisor, and operations executive in the private and public sectors. His career is focused on defense and homeland security issues and technologies. Will earned his PhD in physics from the University of Notre Dame, great NDIA member, and his bachelor's from Hamilton College with a major in physics and a minor in history. So Will, happy to have you with us today. Appreciate you taking the opportunity, taking this chance to teach us a little bit about GPS, and over to you for your presentation.
Thanks, Arun. Let me share my screen here. Okay, I assume everyone can see it now. So thanks for the invitation to speak here today. As Arun said, I'm Will Bowder. I'm with the Government Accountability Office. Our office, for those of you who don't know, is a legislative branch agency. We work directly for the Congress. Our primary function is we look at the performance of federal programs and look at their management and cost savings and ability to improve. But our team, the SCAA, stood up in 2019, so it's about 5 years old now, has, in addition to looking at technical programs, has a special mission to look at emerging technologies and provide a variety of products, including our technology assessment line, which are sort of deep dives into technologies. So I'm going to be speaking today about sort of an overview of the GPS operation, as well as sort of the context in the DoD, threats to the GPS, and then sort of what we can do about it in terms of alternative position navigation and timing. So I'll also just say that, so see if my slides advance here. So here's some selected GAO work that we've done on both alternative PNT and on GPS and GPS modernization. So I'm drawing a lot of my talk today from these different reports, if you want to go back and look at these and look them up for some more details. Okay, so what is GPS? So the Global Positioning System is a satellite system that provides position and time information to over 1 billion military and civilian users now. You're familiar with it, it's ubiquitous in your everyday life, as Arun says. It currently consists of 31 satellites operating in medium Earth orbit, which is about 12,550 miles above the Earth. Although a full constellation for full coverage of the globe requires 24 satellites, they have 31 as spares if there's issues and come off that they can move them in and offline. They operate in 6 orbits or orbital planes as they're called, and each satellite completes 2 Earth revolutions per day. So it's got a 12-hour period. Coupled to the satellite system is a ground control system where they monitor the position of the satellites and provide updated information to the satellites on board to distribute. And then there's the receiver segment, where every device that uses GPS has to have a receiver in it, and we'll talk a bit about each of these segments going forward. I'll say that the system is currently maintained now by the US Space Force, and the government maintains it, does the upgrades, maintains information, and then distributes it as a free service to all users across the world, as well as to the US military. So a ludicrously brief history of GPS. It was first developed in the 1970s, and the concept was to have satellites broadcasting signals. I kind of think this is interesting because we had already gone to the moon by the point that we realized that we could put satellites up to do navigation in the sky. In 1978, they launched the first Navstar satellite, which was the precursor to the GPS system, and they had a few satellites up there for testing for several years. 1983, they made the growing constellation of satellites available to civilians. But in the 1980s, they operated on a selective availability system where they would deliberately distort the signals of GPS for civilian use. So there was a separate military and civilian signal, and you had worse performance in the military, in the civilian use signal. In 1999, I just sort of put this on here, the first GPS cell phone was deployed. And obviously, this is sort of paving the way to the way we all use it today, that it can be in the hands of literally everyone. And then in 2000, they ended the selective availability. So you have this confluence of events here where now you can start to get individual handheld receivers people can use. And you have now all of a sudden a 10 times improvement in the position availability. And we'll talk about the accuracy of GPS. Then throughout the 2000s, the price of receivers, the little chips, and the associated electronics begins to drop. So now you've gone from a product that costs thousands of dollars to dollars or tens of dollars to get a GPS receiver into your electronics. And so the use just continues to explode from there. And then in 2005, they began the process of modernizing it to be able to provide increased service. So how does GPS work? So this is the technical part, and I'll just say that if you're, and I take it that you're probably not, but if you're a satellite navigation expert, this will be an extremely disappointing summary for you because there are many layers to the operation of the GPS system. But I'm going to kind of cover the top layer and give you a sense of how this works, and then talk about some of the implications for its structure. So essentially, you have a satellite orbiting the Earth. The satellite has a clock on board it, an atomic clock that's keeping track of it, and it also has information about its position within the sky and its position in the orbit. We call this ephemeris data. So the satellite is constantly broadcasting a signal out towards the Earth that gives the location of the satellite and the time that the signal was sent. When a receiver records that signal, it gets then the information from the signal, the time it was sent, and then it has a clock that records its own time. And so what you have is you have the time between the signal sent and the signal arrival. Then the signal is broadcast at the speed of light. And there are some minor corrections to that, but it's broadcast at the speed of light. So if you know the speed of this radio signal and the time, then you can get your distance, or more accurately, your range. So I represent this with this red arrow, a red circle here, that you could be anywhere in this range position around an individual satellite. And then, as I mentioned a couple slides ago, the ground stations monitor the satellite positions in the sky, and then they update their position and clock data on board to keep that accurate. So then you can just extend this concept that if you have multiple satellites in the sky, you could look at 3 different satellites and capture your range from each. And this would allow you to do a classic triangulation of your position. If you picture it here with the 3 red circles around it, you look for where those signals meet, and then you have your longitude and latitude and altitude position. And I should say that it's not limited to applications on the surface of the Earth, but if you're on the surface of the Earth, then those are the things you'd be looking at: longitude, latitude, altitude. But you have a problem, which is that you have 2 clocks in play, each measuring the time, one on board the satellite, one in the receiver. And so what if the clocks don't match up? So the spoiler alert, well, it's not a spoiler, because we'll say now that they don't match up because the receiver clocks are often very inexpensive clocks, and they're wrong almost all the time. So the consequence of this is that you actually need a 4th satellite to produce a minimum navigation solution. And won't go into the math behind it, but essentially when you have that 4th satellite, it allows you to not only solve for the longitude, latitude, altitude, but it allows you to solve for time. So this is necessary in order to get an accurate GPS position and time information, but it also has some consequences. In that the benefit is that the GPS system is also distributing its time synchronization to all of the users of GPS. And this has profound implications because some users are only using GPS for the timing information. And the ability to distribute this globally is incredibly powerful. Another benefit that I like to point out about this architecture is that because the system is broadcasting the signals, and there is no communication from the receiver back to the GPS satellite. So unlike your cell phone network, unlike your internet provider, there's not a 2-way communication. It's just broadcasting it, which means that it has essentially an unlimited amount of users that can use the architecture because they're all just capturing the GPS signals, looking for satellites in the sky, capturing their signals, and doing the calculation for your position on the actual GPS receiver itself. So let's talk a little bit about accuracy. So I put here the GPS.gov has information for 2019 is the most recent year, so they're a little bit behind, but has information on all the nitty-gritty details of the position of it. But the take-line message is that GPS is very accurate. It allows you to get a position consistently within 5 meters of where you're at, so about 16 feet. And often it's a much better position than that. Also, the accuracy, the quoted accuracy they have is less than 100 nanoseconds, but I've seen different figures on this. For example, NASA quotes it to less than 10 nanoseconds. And then there's also a consideration that if you do a specific technique called a time transfer, you can achieve even better accuracy. So it's in the billions of seconds accuracy in terms of timing, which also allows it to be accurate in terms of position because you're measuring the time between the clocks. So what affects the accuracy? Lots of stuff can affect the accuracy of GPS. The technical limitations of how accurate your clocks are, how accurately you can measure the signals. Lots of little things under the hood. The line of sight and the geography. So you probably think that in an urban environment, lots of people, you have good cell phone reception, GPS is good, but actually it can be limited because it might reflect off the buildings itself. You have to maintain a line of sight to at least 4 satellites to be able to have a GPS position. And you might be obscured from that, or the signals might be reflected off buildings, which will affect the time of arrival and their travel path. So you can wind up with some inaccuracies, even or especially in urban areas. The ionosphere is a layer of the atmosphere, causes a delay to the GPS signal. I'll say no more about that. And then the receiver configurations themselves. But there are ways to assist this. I won't go into the details of these, but there's assistance for GPS using alternative signals. You can use dual frequencies. There's actually multiple frequencies that are broadcast from the GPS satellite, and they can process. You can use those to improve it. And then there are other things you can help do to improve performance, multiple receiver configurations, stuff like that. So there's ways to improve the performance beyond this limit, and there's also issues that affect the accuracy. So that's sort of the quick and dirty overview of how GPS works. So where does the DoD use GPS? The short answer is everywhere. We have this picture here from one of our reports sort of detailing there's 4 satellites in the sky because it takes 4 satellites minimum to make a GPS position lock. You know, planes, bombers, unmanned vehicles, surface ships, submarines, munitions, individual munitions, and mounted and dismounted soldiers. You know, DoD has said that GPS is the cornerstone of their PNT, so their position, navigation, and timing strategies. So it's ubiquitous in essentially everything that they do. And it also has numerous civilian applications, aviation. So the GPS upgrade is even releasing a special channel now to be able to guide planes. So, you know, your plane is using a GPS, your commercial plane is using a GPS signal to navigate. Precision agriculture, which you might not think about. Your ability to track where you're planting, applying chemicals, harvesting in a field using a GPS system makes it a much more efficient process. Space navigation, things like the International Space Station uses a GPS signal to track its location now. So again, I think it's interesting that we went all the way to the moon and then, but didn't have GPS. And now we have sort of the combination of these technologies. And then I mentioned the precision timing. So things like communications in your cell phone, finance and in trading and high-speed trading applications, they timestamp it all with the GPS signal. Your computer essentially is using time from GPS, and the ability to distribute that time and synchronize it across multiple platforms to the billionths of a second, tens of billions of a second time frame is extremely powerful, and it's used everywhere. And in fact, there was a really nice article. I don't actually can't find the chat amongst here, but there was a really nice article in the New York Times last week talking about all the applications of GPS and what we would do if it goes down. And there's a number of things that we'll talk about some of those scenarios in a few seconds, but it made the point, I think, very nicely that it's ubiquitous. So, but it's vulnerable. So GPS, threats to GPS, basically we can summarize in 2 categories. So there's, first is jamming. The GPS signals are weak. In order to get the coverage of the entire Earth with a manageable number of satellites, they're positioned in this medium Earth orbit position, which is, as I mentioned, 12,000 some miles above the Earth's surface. That means that by the time they broadcast the signal, it hits the surface, it's a pretty weak signal. In addition, it's broadcasting on a known frequency. It turns out that there's only so many frequencies you can use that will get through the atmosphere, and the GPS frequency is well known. So if you have a local signal putting out, a local jammer putting out a signal on that frequency, it's possible to prevent the GPS signal from getting through, and you'll lose contact with the GPS satellites. Spoofing is the other sort of thing to talk about, which is you don't just stop the signal, but you replace it with a local signal that provides the incorrect position information. And this was the pseudo plot of a James Bond movie that if you're like terrible action movies like I do, where in Tomorrow Never Dies, where they had a GPS encoder that they'd stolen and they were using it to steer ships off course. Now, I watched this movie recently after having immersed myself in all this, and I will say that the scientific accuracy was so-so, but the principle is still there that you could use an alternative signal to essentially change the navigation of ships, but with a spoofed signal. So what do we do about this? And this is a focus of a lot of DoD efforts at the moment, is that so there is a PNT technology roadmap, and essentially the conclusion is no single PNT system is capable of supporting all the DoD's requirements. And so they basically have 2 strategies to deal with these threats. One is make GPS more robust. So we can improve the GPS in ways that we can get around the jamming and spoofing risks. And the second is we need different alternative technologies to be able to get the position, navigation, and timing information without using GPS. So I'm going to break down each of these as sort of my last segment of the talk here. So GPS resiliency. So this is, as I mentioned, in 2005, DE launched what they call their GPS modernizations programs. And then this current efforts revolve around a system called M-code, which basically is a separate military code signal that is designed to reduce the risks of jamming and spoofing in several ways. Broadly, it has a stronger signal with a different spectral profile. So it's got a different sort of frequency profile, if you're interested in the technical details of it, that's resistant to jamming, and that it will allow them to resist jamming attempts. In addition, it's cybersecurity is a big focus of the M-code program. So it's more cyber hardened so that it's not easy to hack in and spoof the signal. As you can kind of imagine, if you think about it, that these types of upgrades basically mean that you have to upgrade each segment of the GPS system, the control station on the ground, the satellites, and the receivers. They all have to be able to broadcast and receive this information and decrypt this information appropriately. So this is a massive undertaking for the DoD, and we consistently examine this program and provide update reports, and some of those are listed in the second slide of the talk. So update the space systems to be able to, the satellites, to be able to broadcast the GPS M-code. Currently, they have 25 of the 31 satellites able to broadcast M-code. The requirement could rise to 27 instead of 24. This is somewhat of an open debate right now. And then there's additional cost. And then there's also plans beyond the ones that already deploy M-code to replace some of the older M-code systems with newer ones. So the combined effort of a couple of different programs here, both what they call the Block 3 and the Block 3F satellites, is about $16 billion to upgrade the satellites. The ground control station also needs to be upgraded. It needs to be able to speak to these new satellites. And as I said, it provides tracks their position, it provides information, make sure they're synchronized. It can make deviations. If a satellite moves off course, it can move it back on. So all these sorts of things. So the upgrade to the ground control station for the new satellites, what they call OCX, the OCX ground control system, is about $7.4 billion based on our recent reporting. And then there's the receiver end. And this is, I put some figures here, but it's a massive undertaking, as you can imagine. You have up to 1 million new receivers over 700 different platforms. That's vehicles, handhelds, munitions, all these things need to be upgraded to decode the M-code signal. So DoD currently has, their plan is to do this in a set of blocks. They're currently testing a set of cards receiver cards. And I sort of put the geometry of how this works. There's a chip that they put on a card, into a receiver, into a platform. Up in this graphic at the top, they're currently testing the first 4 systems and report on that. And then the second, they're starting the increment on the second system. So I believe it's something like 4 systems in the first one, then an additional 50 systems, and then finally tackling deployment to the full 700 systems. So it's a massive undertaking. There's $1.4 billion on the development of the increment 2 system alone. Calculating the procurement costs and whatnot is still an open question. And those, of course, are, it's expensive. It's going to be an expensive, massive undertaking. In addition, we've reported on numerous challenges and delays that they've experienced over the course of deploying this M-code system. So I talked about there's unclear requirements about how many satellites they need. There have been delays to the test evaluation of the receiver cards, even getting these first 4 cards out. In a recent report, we discussed, a potential unsound business case for the handheld receivers and whether or not those were still necessary, and then delays to the ground control station deployments. So it's a massive undertaking, and there's lots of delays, and it stretches. Of course, U.S. Space Force runs the system, but all of the services need to have upgrade cards, and they all have programs that are sort of looking at upgrading their systems and platforms to the M-code system. So great if we can make GPS more resilient, but it's challenging. So the alternative option is to build alternative technologies. And the way I sort of explain this is to think about, okay, there it is to think about your cell phone. So your cell phone has a GPS receiver in it, but it also has cell towers, it has Wi-Fi, it has an inertial sensor inside of it, which is tracking, like if you run with your cell phone, it's tracking it. That's how it tracks your steps, unless it's using the GPS system, of course. But it has all these different sensor modalities in it, and so there's two sort of ways to do it. One is sort of relative PNT that I call, which is you could track your position and your time on your individual platform from the time you lose GPS lock. And then alternatively, you could use an absolute PNT system, which I'll call it, which is you use an external signal to do the position calculation, similar to the way GPS does, but you might use cell phone signals. You might, they've looked at using Wi-Fi signals. So those are two sort of different approaches, and I'll talk about each one of those. So in the relative PNT realm, again, the principle here is that I've lost my GPS signal, it's been jammed, it's whatever, I'm in a place where it's not accessible. I essentially track my position and my time myself. So the primary sort of position that they will use for this is what they call an inertial measurement unit. So these are essentially sensors that detect the acceleration of the individual platform. Again, these are in your phone. That's how you know when you turn it, the screen turns, those types of things. It tracks your steps. That's how it knows that. Essentially, if you measure these accelerations and you keep track of the time, you can calculate what your position was in any given direction since you last lost GPS. And there's a trade-off here, because the better the system you build to do that, it's a tough thing to do. I'll just say that, to cut it short, it's a tough thing to do. And the better the system you build to do it, the more expensive, the more power consuming it's going to be. So DoD has efforts, programs looking at low cost sensors using a so-called microelectromechanical devices to do this that might fit into a chip scale. And then they have higher precision devices that will actually use quantum sensors to do this. So these are actually using atoms and putting them sort of into a device, and they actually will use the atoms themselves to measure the inertial changes they do. And that has a higher precision, but that comes with a higher overhead of being able to do that. There's infrastructure, there's cooling, there's power requirements. So they're looking at high precision and lower cost sensors. And again, the trade-off is how long you're going to be able to maintain your position without GPS. In addition, you need to keep track of time, not only to have the time yourself, but the time is an important element of coupling with the inertial measurement unit to keep track of your position. So again, there's a wide range of technologies they're pursuing. I show down here in this figure, there's a huge range. So on the left of this figure, these racks are the atomic clock with the United States Naval Observatory, the master clock that's distributing time up to the satellites and to GPS, and that we're all basically synchronized to some degree of precision right now. So this is a series of atomic clocks that takes up an entire room. It's incredibly accurate, but not very portable. And on the other side, there's programs in looking at chip scale atomic clocks. And you can see here one of the chip scale atomic clocks under development by the DoD now. And that's aiming to have, that maybe has a precision of, I forget the exact precision, but it's somewhere in the neighborhood of 10 times worse than GPS. but it's able to fit onto a platform. And so this is all about trade-offs of the size of the platform and the ability to do it. So larger platforms like surface ships, carriers, they might be able to have rack-mounted atomic clocks on them to be able to keep track of this, but smaller platforms and handhelds will need some sort of solution. Okay. All right. So advance my slide here. So the alternative approach is to use an absolute system. Okay, so it would be very nice if we could all just have a GPS precision tracking system within us. We would measure our inertials, measure our clocks, and keep track of that, but it's just not practical. So there's going over some period of time, whether it's minutes, hours, a day, you're going to lose synchronization. You're going to lose your ability to keep track of your position and your time. So the concept of the absolute PNT portfolio is to basically reset those onboard measurements with another external signal, some sort of external signal that's not the GPS signal. So there's two sorts of approaches. One is you could use a passive signal. So these are things like celestial navigation, which obviously is extremely old, but they have automated systems now that they're pursuing that are able to track the stars even in daylight and determine your position to an accuracy of maybe about 50 meters. Magnetic systems. So the Earth has a magnetic field, and there are variations in that magnetic field. And you can map that out basically as if, just like you can map out geography or topography, and you can use the features in that map to be able to track it. And this is an avenue that DoD is pursuing as well. And you could get currently about 100-meter accuracy with this. Similarly, you could use what we called terrestrial image analysis. There's various different terms in it, but that's what we sort of coined it in our report, which basically means you put a camera on your platform, you look around, and you do an image matching to the area that you're around. And this is achieving sort of the best precision. You get about maybe 10-meter accuracy. So for example, if you're standing in Washington, D.C., and you look and the camera looks around and you see the Capitol on one side and you turn around and you see the Washington Monument on the other, you can look at the relative shape and size of the Capitol and the Washington Monument in your screen and use that to determine how far you are from each and what angles you are in there. So it's quite an interesting technology, and they have algorithms that process the images and do this automatically. So none of these I mentioned are sort of achieving the same precision as GPS, but they're able to provide this reset. They're all based on the principle that we can make an external observation, compare it to a known map, and get some precision. And there's different applicabilities. Even though they don't have the same precision, they can be useful in different situations. If you are, for example, in an urban environment, the terrestrial image analysis would be very useful because there's lots of features and landmarks you can look at. If you are in a desert, that's not going to be so useful. So maybe you need something like a magnetic platform or celestial navigation. And there are different accuracies that they need in different circumstances. The other option is an active signal. So this would operate with a different radio frequency signal that's based, well, I shouldn't say this, a different radio frequency signal, and use the same sort of process to triangulate your position as you do with the GPS signal. The advantage is that some of these signals might be stronger than the GPS signal, and so they would be harder to jam or to spoof. So one option is to use very, very low frequency with VLF radio signals. There are beacons set up around the world. DoD has an effort looking at using those to triangulate your position. The advantage of those signals is that they bounce off of the ionosphere, and so they can travel quite a long way. Another possibility, and this is sort of flitting in and out of the news, is using low Earth orbit satellites. So as opposed to being up in the medium Earth orbit, if you're lower to the Earth, that's the closer the signal is, the less diluted it's going to be, so that's a stronger signal that's more resistant. The downside to this is you need a lot more satellites to be able to cover the globe when you're operating a low Earth orbit constellation. So the concept is not sort of an either or for the DoD. It's really sort of a holistic PNT concept. One is that we use a complement of the relative and absolute solutions when GPS is denied. So we have some better sensors on board that can track our position. We use some external signals that can help recalibrate those sensors when we're still GPS denied. And then we have, and then coupled to that, we improve the capability of the GPS system by implementing the M code, which helps reduce the risk that GPS is denied. There's no silver bullet to this. It's sort of a complement of technologies. And one thing that we stress in a number of our reports is the need to develop both of these technology arms. So there's no silver bullet. We're going to need a lot of lead bullets. So the continuing challenges, just to sort of highlight at the end here to this, this is a complex series of programs. M code has been a big focus of modernization for the last couple decades, but there's changing requirements. There's operational test challenges that are delaying it. And even once complete, I think it's fair to say that M code will not fix everything. There are limits to how much it will be able to do. In addition, there's a challenge of but one of the things that we point out is that there's a challenge that there's a prioritization of modernization of the GPS system over alternative PNT. So even though there's delays to M code, even though there's limits to M code, we still prioritize that over alternative PNT. And one of the policy considerations and recommendations we've made is to have the PNT Council, which is supposed to govern the trade-off of these, look at the prioritization. The additional problem is that there's a diffuse responsibility for upgrading GPS and developing the alternative PNT across the services. This results in a prioritization of the modernization efforts, potentially to the detriment. And the final point that we sort of talked about, particularly in our technology assessment on alternative PNT, was the concept of there's an over-reliance on GPS potentially. And this is something that New York Times article talks about a little bit, is that it's ubiquitous, it's everywhere, and if it goes down, what are we going to do? Again, if we're not prioritizing alternative PNT, both in the military and then also on the civilian side, which I won't touch on in this talk, but we're really over-relying on GPS. It's so convenient, it's free, it's everywhere, it's cheap to implement. So one of the questions we've sort of raised is, does this make sense to continue moving forward with a GPS-centered architecture, or do we need to prioritize some other alternative navigation solutions that might be more resilient than the GPS? So that sort of brings me to the end of my remarks here, and I see the question and answer sections blowing up. I tried but failed to manage it during the course of my talk, so I'm happy to walk through all of those at this point.
Hey, well, thanks for the presentation. It was really great. Like you said, there's a lot of questions here, so let's fight our way through some of them, if that's okay. I'm going to go in no particular order. So how do the satellite constellations from other nations, such as China, Russia, EU, compare to our GPS system? What are the names of those?
So there's 3 major constellations out there. The Russian GLONASS system, the Chinese have the Baidu system, and the European Union has a system whose name I am totally blanking on in the moment, but maybe I'll Google it off screen.
Galileo?
Galileo, thank you. Yes, that's the one. So there are various degrees of functionality compared to the GPS. I think it's fair to say that So some of the constellations are still being built to the best of my knowledge. I think the Russian one has a complement of 24 satellites. I think Galileo is still building up to that, last I was aware. So, you know, coverage is not necessarily at 100% like it is for GPS. In addition, I think that GPS is still leading the way in terms of the accuracy. One thing I think about is the contribution to it's still, suffice to say, I think it's still leading the way in accuracy. There are other systems people don't want to be. I think I saw a question in the chat about like, is GPS open to everyone? Yes, GPS is open to everyone. If you're from another country, you can use it. It's globally open as long as you have the receiver in your equipment to decode it. So it's still used. It's still the leading standard, but there are other systems out there. There are also regional systems of GPS regional systems of GNSS, which is sort of the generic term for a global navigation satellite system, I believe. And so there are regional systems that I think India has one, I think Japan has one that they cover only specific areas of the Earth. So it's expensive and it's technically complicated to put one of these systems up. So GPS is still, I think, fair to say, leading the way. I don't have the exact precision numbers off the top of my head, but you know, it's still the best.
And those other systems and other run by other nations or the EU, are they open like the US system, or do they block the signal from non-national users or anyone?
You know, I believe that they are open. I believe that we could use those other signals as well, and I think in some instances we do, but I'm not. I know the Galileo system is. I'm not 100% on the other ones, but I believe they're open. Yeah. And
I think you touched on this a little bit, but the in general, the approach for our allied nations and for the civilian infrastructure that maybe the military depends on, national security apparatus depends on, are they using M-code or are they using the civilian signals?
Yes. So, I mean, M-code is sort of there. You have to have receivers for M-code, and it's not actually deployed at the receiver level yet. I think it's still an open discussion whether we would open M-code to our allied nations, but that would specifically be for military users. So the civilian population would not be able to access it. It would be encrypted in a way that they couldn't access it with a civilian receiver.
There are a few questions on M-code here.
Sure.
So could you just, in a couple more sentences, how does M-code actually assist in counter jamming?
Yeah. Okay. So this is kind of cool. So one, the simplest way to explain it is that it broadcasts at a higher signal intensity. So there's more power going down to the Earth so that it's more resistant to being jammed. So, I mean, it's just, if you have a competing signal, that jammer has some sort of range. If the M-code signal is stronger, it can do that. But that's limited because the satellite is broadcasting the signal and it needs to have enough power reserves to be able to broadcast that signal essentially indefinitely on board the satellite. So the other way, though, that M-code addresses the jamming is it has a different sort of frequency profile. So when you look, so there is a central, I'm going to try and do this as non-technically and accessibly as possible, but essentially, when you look at this, at the shape of the GPS signals across the frequency, there's a centralized frequency for each GPS signal. And as I mentioned, there's two of them, but they also sort of, there's a range of frequencies that they cover, and there's a space of that. They're mostly centered around that central frequency, like the most intensity is at that central frequency. M-code uses a different approach that divides it into a broader frequency with less intensity at the central. So if you are jamming and you're trying to jam, 1500 megahertz, then M-code has more intensity outside of that to be able to resist that jamming. So it still gets through unless you have a jammer that's matching the frequency profile of that code. So, in theory, you could, it's more resistant to jamming in that way. So it gets deep into the technical details, but hopefully that, it gets more complicated from there. I promise you, but hopefully that gives you a sense.
If DoD switches to M code, how does that affect civilian users? What's the impact on the cell phone network? As I assume that you do that when GPS is jammed.
Yeah, let me clarify a couple things and then unpack that. So the civilian signals would not be affected by M code. So the GPS, every GPS satellite is going to continue to put out the civilian signals. There's already a military signal put out by GPS, and so this would just be an additional signal. And as I mentioned, GPS is expanding the civilian signals to include this special, air traffic signal. So, and as far as I know, and I think DoD said that they have no intentions of discontinuing the maintenance of the civilian signal. So it's simply adding another thing that is put out. There's another antenna, another system putting out a signal to it. So that would not be affected. And then your question on the cell phone network, and then your question on the cell phone network and the jamming. So I'll just say that jamming is generally a localized phenomenon because you need to basically, it's again intent on putting out enough power to overpower the GPS signal, and you can only do that over a regional area. The cell phone network is not broadcast by the GPS system. That's totally separate from it. So that uses ground-based towers. But there is something called cell phone assisted GPS, where essentially you would use the cell towers on the ground to help assist to triangulate your position. And as I mentioned, this is particularly prevalent in urban areas. Think of New York City. Like when I say you have to have line of sight to the satellites, that's exactly what it means. You have to be able to look at the sky and see at least 4 satellites, and you don't always have a clear path to them. So you can use some of those signals to do it. But in terms of the cell phone network, it's separate. The only thing I mention is that the timing from that network is ultimately distributed via GPS. And so the communications would be disrupted if we didn't have GPS to distribute that, because and there are alternative ways that they're looking at distributing time without GPS, but as far as I know, those are not widely deployed.
So you talked a lot about M code as making the system resilient, at least for the military side.
Yeah.
But if the satellites themselves are damaged by natural forces, by an adversary, the GPS signal goes out for everyone, military and civilian. Is that correct?
Yep.
And how many of our satellites could we lose before we lose the system?
Such a good question. So there's 31 deployed right now. It takes 24 to have global coverage. So nominally you've got 7 spares, seven spares, but they're not all operational at the same time. Like some of them are phased in and out because they need upgrades, or they need to be recalibrated, or they're not broadcasting correctly. And all of this information about which satellites are healthy and broadcasting correctly is delivered by the satellites to the users. So as a user whether you should trust the signal coming off of a satellite or not. But if you lose more than that, then, and I'll just sort of, talk broadly here, then yeah, you're losing coverage, right? So you're losing, coverage of the globe. In theory, if you are at a point where you can still see 4 satellites, you can still get the information. But, if those satellites move out of view over the horizon, then you lose lock on that. So I know that's a bit speculative, but that's sort of the sense that you have.
Along those lines, the current satellite constellation, it provides global coverage. Does it provide global coverage equally across the globe, or is it designed in a way to prefer certain parts of the globe?
As far as I know, it's equal across the globe. There may be slight exceptions to that, but I believe you can actually look this up in their report, but the details are very technical. But they do measure reliability every year across the globe and making sure that they have at least 4 satellites in coverage up to whatever their metric is. It's like 99.9% of the time. So they're divided up in planes, though. So the orbits that they take and the positions in those orbits are divided up to have global coverage.
Who maintains the GPS satellites?
Space Force.
And so it's part of their, I assume, operations and maintenance annual budget.
Yeah. Yes. So there's, so they maintain. So yeah, the maintenance of that is paid for by them, and then there are of course these separate programs looking at the upgrades, specifically for the M code and things like that. So
there's a few questions on the PNT side of the house as well. So you talked about atomic clocks. Are there quantum sensors being currently used for this, or is the science not there yet? Can you discuss potential defense applications?
Yeah, so there are quantum sensors being developed for these inertial measurement units. So atomic clocks are kind of like quantum sensor 0.0. And then inertial measurement units doing quantum sensing are kind of like quantum 1.0. And then things like quantum cryptography, quantum communications are sort of beyond that. So there are sensors being developed that basically look at essentially what you do is you have a ball of atoms that are sort of free floating. You have a laser and cooling system, and you move them, and then you look at their deflection based on the acceleration that they feel from it, and that allows you to very precisely detect it. So there are those are definitely in development, and I would say I'm trying to think off the top of my head if there's any sort of pseudo quantum ones deployed, but I would say those are potential near-term applications. But the size is somewhat limiting. Whether you can get those down into the handheld size is a question, because it just requires a lot of engineering to get them smaller, but they're definitely under development the last time we took a look at this.
So we're running out of time here, so we're going to go to speed lightning round here.
All right.
Are Russia and China developing alternative PNT systems, and where are they relative to us?
To my knowledge, yes. I do not know where they are relative to us.
You talked about terrestrial imaging to be an augmentation to the signal. Is current terrestrial imaging good enough to support this, or do we require significantly more detailed mapping and imaging?
Yeah, I think as we looked at it, I think the question is, do we need more maps to be able to match them to? And the answer is yes.
You talked about potential over-reliance on GPS. Are future defense systems being designed to not just rely on GPS, or these requirements being included in programs and contract language?
I think the focus in the DoD is still on, and I don't want to misrepresent them, but I think the focus is still on GPS. It's still their cornerstone. And one of the things that we would say is that there's not enough of a focus. There are alternative PNT programs. They are funding this, but it's not as prioritized as the GPS upgrades.
Could you achieve all of these same effects with a distributed grid of cheap, small satellites? What would be the pros and cons of that?
Yeah, such a great question. In principle, yes. So they're looking at low Earth orbit satellites. They could do this. They have stronger signals. The challenge is that that you can't just have any satellite do navigation. It's got to have that onboard information that's precise enough to do GPS, and you can't. And they're faster moving, so it's more difficult to keep the ones on. You have to have a big enough network to keep enough on the horizon to be able to do the calculation. That's the very short lightning round answer.
And okay, last question. You commented about GPS satellites adding a special channel for commercial aircraft. This is not a lightning answer, I suppose. Can you expand on what that is and when it will be deployed?
Yeah, essentially, maybe no is the answer. I can expand on that. It's not something I've tracked very detailed. It may actually, they may actually have already deployed it, but I think that they did actually deploy it. But essentially, it's it's just an additional sort of channel and signal dedicated to the aircraft navigation.
So with that, Will, I'm going to have to call it quits. There's still more questions piling up in the Q&A box, which shows that this was a great presentation. We really appreciate your expertise and that clear presentation. Thank you for that. Thank you also to all of our guests for their attendance and all of the great questions. We're going to post this recording online as soon as possible. If you have feedback about this event, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I also want to take this opportunity to highlight a few ETI upcoming events. The first is the FY25 DoD S&T Budget Priorities webinar, where Undersecretary Heidi Shue and the Service Science and Technology executives will be presenting an overview of their FY25 S&T budget request, and that'll be on April 30th at 1 p.m. Go to ndia.org/events for registration information on that one. The next Tech 101 will be on generative AI, and that'll be on May 15th at 1 o'clock. Again, ndia.org/events. Following that, in June, we'll be on trustworthy AI. And then I want to talk about the second NDIA Emerging Technologies Conference. It's scheduled for August 7th through 9th at the Washington, D.C. Convention Center. It's building off of last year's inaugural event, which was completely sold out. Registration will be open in May, and so please don't be late. Confirmed speakers to date include Deputy Secretary Kathleen Hicks, Vice Chair of the Joint Chiefs of Staff Admiral Grady, and Undersecretaries Heidi Shue and William LaPlante. The conference will focus on how we can move emerging technologies more rapidly from research into production and use, with a special focus on emerging technologies, as well as missions like JADC2, contested logistics, and counter UAS. There's also going to be a special track of programming on the operational challenges and technology needs facing EUCOM, AFRICOM, and NATO. Last year's event, like I said, sold out. Registrations, exhibits, and sponsorships. Look for more information on all of these opportunities, plus the opportunity to present your own work at this conference coming soon in May. Also, the Emerging Tech Horizons podcast is available on YouTube, Spotify, Apple Podcasts. You can see the YouTube link there. The episode this week is on budget reform, on the Planning, Programming, Budgeting, and Execution Commission's final report. Will be upcoming episodes on partnerships with India, the Index X program. And on that slide, you see previous examples of programs on what's in the National Defense Industrial Strategy, what's in the National Defense Authorization Act. Hope you tune in and subscribe to that podcast. With that, I just want to thank everyone for joining us again today, and once again, thank our speaker, Will, for such a great presentation.